হ্যাঁ, তুমি ওটা বলে দাও।
হ্যাঁ,
ওরা মাইক অন করতে পারে।
হ্যাঁ
হ্যাঁ, ওকে করেছি। বলছি স্টার্ট করার পরে ইনভিজিবল হয়ে যাব আমি, কারণ তাহলে ব্যান্ডউইথ প্রবলেম কম।
আচ্ছা
ওকে, প্লিজ ক্যারি অন, আমি ওয়েট করছি।
আচ্ছা ঠিক আছে।
I don't know this, but again, let me show you.
তাহলে আমরা এবার প্রোগ্রামটা শুরু করতে পারি।
শিওর।
ইউটিউব লাইভটা স্টার্ট হচ্ছে কিনা এবার দেখি।
শুরু করবো?
হ্যাঁ, লাইভ স্ট্রিমিং শুরু হয়েছে তো? হ্যাঁ স্টার্ট হয়ে গেছে। ওকে
স্টার্ট হয়েছে।
তাহলে ম্যাডাম এবার শুরু। হ্যাঁ।
Good afternoon, everybody. I, Orpita Bose, welcomes you all in the first day of the two-day webinar on behalf of Physics Department, Ashutosh College. The webinar will be on 27th and 28th August, which will deal with very contemporary subjects, and hope you will appreciate these. Today's talk will be on the role of symmetry in physics, which will be given by eminent scientist Professor Bishwarup Mukhopadhyay of IISER, Kolkata. Sir, our heartiest welcome to you in this webinar. Our Vice Principal Sir, Professor Apurva Roy, and Vice Dr. Manush Kobi, not been able to present here due to their official engagements, but they have sent their best wishes for us. We are very pleased to welcome Dr. Kathagato Raichaudhuri, the IQAC coordinator of our college, in this webinar. Now I request, before starting the webinar, I request all the participants to mute your audio and video throughout the webinar. If you have any questions regarding the talk, then please write it down in your chat box or comment section, and we are actually deal with that, and relevant questions will be answered by our speaker after his talk in the question answer session. Okay. Now I welcome Dr. Kathagato Raichaudhuri, the coordinator of IQAC cell of our college, to give his welcome note.
Hello. শোনা যাচ্ছে? Hello. Okay, thank you, Urpita. It's my honor and pleasure to welcome all of you to the first day of the two-day seminar being organized by the Department of Physics. It is my pleasure to welcome Professor Bishwarup Mukhopadhyay of Department of Physical Science, IISER, Kolkata, who will be giving the talk today. I'm sure that you all will have a wonderful time listening to him. I would welcome all the participants, the students, and the faculty members of the department in this seminar. And I would like to thank the departmental staff and the IT team for organizing this webinar today. I hope you will have a wonderful time. Thank you, sir, again for your participation. Thanks to all. Thank you.
Thank you, Tathagato. Now I will request our head of the Department of Physics, Dr. Surya Sarathi Bhattacharya, who is also the convener of this webinar, to say something about our eminent speaker and give his introduction for the speaker. Surya.
Good afternoon and welcome everybody on this very first day of two-day webinar of Physics Department, Ashutosh College. It is my pleasure and honor to introduce today's speaker, Professor Bishwarup Mukhopadhyay, HAG Professor, Department of Physical Science, IISER, Kolkata, former Senior Professor at Harish Chandra Research Institute, Allahabad. He is a well-known high-energy physicist known for his research on high-energy colliders, Higgs bosons, and neutrino physics. An alumnus of Rajabhaja Science College, Calcutta University, has done reportedly notable work on theorizing gauge boson fusion as the dominant mode of supersymmetric particle production. He has published more than 200 high-quality research articles in journals like Journal of High Energy Physics, Physical Review D, and Physical Review Letters. He also has edited a book entitled Physics at the Large Hadron Colliders, along with Professor Amitabh Datta and Professor Amitabh Rai-Chaudhury. He is an elected fellow of National Academy of Science, India, Council of Scientific and Industrial Research, the apex agency of Government of India for scientific research, awarded him Shanti Swarup Bhatnagar Prize for Science and Technology, one of the highest awards for his contributions to physical science in the year 2003. Now, I would like to request you, sir, to present your talk. Sir, we cannot hear you. Your mic is muted.
All right, thank you. Thanks again. So thank you very much, Surya, for setting up this whole talk. And I must thank my very old friend Manorama, Professor Manorama Bhattacharya, for contacting me for the second time to take part in deliberations in Ashutosh College. And finally, I thank all the participants for assembling for this discussion in these difficult times. Now, since the time is difficult, the time that we are passing through is difficult, I don't want to talk about something very intricate. And I will also not talk about any very recent development and research. Instead, I will confine myself to a discussion on some principles, or rather some concept making its way around most principles of physics, be it at the basic level or on cutting edge issues. Now, a good part of the talk will be really confined to practically high school physics to illustrate the concept I'm emphasizing. Towards the end of the talk, I'll go to a few somewhat advanced topics. Before I build up to the concept called the concept of symmetry, let me just remind ourselves what physicists do. Physicists want to explain natural phenomena concerning matter and energy, but that explanation must come in a quantitative way or in terms of experimentally measured number or measurable numbers. It is in terms of such numbers that we accumulate our experimental observations, and the aim is to achieve explanation, interrelation, and correlation of such observations through a mathematical structure, which finally takes the shape of a theory. And theory not only explains observations, but also predicts and correctly predicts, if it is correct, the outcomes of subsequent experiments. And if such subsequent observations are numerically corroborated, then the theory gradually becomes a law. Not to say that law is ever unchanging, because change is the hallmark of scientific development. Therefore, if there is some new phenomenon which the existing law or existing laws cannot explain, or if there is some logical inconsistency in the mathematical structure prevailing in the existing theory, then the law or the theory will have to be either rejected in favor of new ones or modified to accommodate new observations. Just like Newtonian mechanics reigned supreme in classical physics for several centuries, till it was found in the turn of the 20th century that in the microscopic world they lead to not only theoretical inconsistency but also experimental observations that it could not explain, and thus was born the new logical structure of quantum mechanics. Now, of course, once the starting point is sort of identified, may I go to the next slide now? Are you on the next slide, Sujya? Are you on the next slide? Please go to the next slide. All of the contents of the next slide have already been said. Please roll down all the way to the end of the slide. Further. So I have come up to this point. So next, let's go to the next slide. Oh, okay. So, in fact, I think life will be simpler if you slide down to for the entire slide with all the items. I'll in my way cover them. No, back. Okay. So, can someone admit the new entrants? My screen is interrupted every time. Okay. Now, I spoke about mathematical structures constituting a theory, but what is the starting point? From what do I feel inspired to set up a particular theoretical structure based on observations? Unfortunately, there is no specific rule on that. You have to depend on your scientist's intuition and also very closely and very minutely on experimental data, which constitute the gamut of the most sacred objects to scientists, sacred in the true sense. Honest adherence to data is the ultimate thing. However, even with available data, setting up a theoretical structure is a matter of great challenge. A guiding principle here has all along been the consideration of symmetry, and that's what I'll speak about. Symmetry basically means that a system does not show any change, or rather stays unaltered under certain operations. And for this purpose, let us talk about mathematical operations. So if we go to the next slide, the mathematical operation here is reflection about the vertical line at the middle, the black line, under which the left part goes to the right and vice versa, and nothing changes. So therefore, this picture, our system here is this picture, this has a reflection symmetry about the central vertical line. Now, go to the next slide, please. If we look at this picture, here also there is a symmetry, but you notice, if you, for argument's sake, consider this to be a square, you will notice that you have the thing unchanged under rotation by any multiple, positive or negative, that is a left rotation or right rotation of 90 degrees. So this picture has a bigger symmetry than the previous one. Now, if you go to the next slide, now you see a circle. It has a much bigger symmetry. It is unchanged under rotation by any angle about an axis passing through its middle and perpendicular to the plane, any angle from 0 to 360 degrees. So it has a perfect rotational symmetry. And since the angle of rotation can be any continuously taking values from 0 to 2 pi, this symmetry is called a continuous symmetry as against a discrete symmetry which characterized the two previous figures. Now, such symmetry is not necessarily confined to geometric figures. It is there in terms of some mathematical functions as well. If we look at the next slide, consider a function y of x is equal to x squared. According to our definition, it is symmetric under x going to minus x, just like some angle theta being there, f theta equal to sine theta is symmetric under theta going to pi minus theta. Similarly, cos theta has a symmetry, and a function like fz of a complex number, like fz equal to z star z, which is the modulus squared for the complex number, is symmetric under an phase transformation of this kind on the complex number z. So mathematical functions, which by now we know to be the essential constituents of all mathematical structures of theories, they are also liable to showing symmetric behavior. And these, I emphasize, can be extremely valuable in having a clue to the particular mathematical structure leading to the construction of a theory. Next slide. For example, certain structures found in nature show symmetries. Look at an ammonia molecule. It's a three-dimensional figure, so it's looking asymmetric, but it has a what are called tetrahedral structure with a nitrogen molecule at the apex, and certain specific rotations will take one hydrogen to another, and the structure will remain unchanged. This is a demonstration of a symmetry observed not in any picture drawn by human beings or any sculpture set up by human artists, but in nature itself, in molecules that are already seen. Similarly, if you go to the next slide, you see the atomic constitution of sodium chloride, which lies on our dining table all the time. There are sodium atoms and chlorine atoms in alternate positions in cage-like structures, where you see that a shift by a fixed position, fixed distance, one chlorine atom goes to another, and similarly sodium atom going to another. So a pattern repeats itself in crystalline structures like this. This is another symmetry, namely crystalline symmetry or lattice symmetry, the repeated patterns being called leitmotifs. These are also there in many physically occurring objects, which make us curious about the origin of such structure naturally coming up and the physics laws underlying them. Next slide. Now, as we have already indicated, if certain mathematical functions and expressions are found to be the driving principles of certain laws of physics, then the laws of physics constructed out of them should display the effects of such symmetries, and certain invariances or invariance under space operation or time operation or rotation or something will be reflected under such laws. Next. On the other hand, if you go the other way around, look at naturally formed structures like the ones we have seen already, then you will expect some symmetry lying hidden directly or indirectly in the physical laws responsible for their formation. So both ways symmetry is driving us, from observation to the formation of laws, and from the underlying mathematical structure of a physical theory to the consequences of the theoretical predictions. Next slide, please. We examine several examples of this one by one. Since there are several examples in my set of slides and we have a finite amount of time, I may skim through or just pass by some of them while I may concentrate a little bit on a few more. The first one is a simple pendulum which undergoes simple Herm motion, and consider this in the absence of any air resistance. Please go to the next slide because this picture is familiar to everybody. Please complete the whole slide. Okay. Now, if you solve the equation of motion, which in a somewhat concise way I have written as the second line, we know that this is the solution to the equation. And the solution shows such properties that as time as time advances, this position of the pendulum, the bob of the pendulum, periodically comes back to certain repeatable positions. There is a symmetry in the solution as it is there. What can it be connected to? It is connected not very visibly to anything at this level, but the potential which is responsible to make the equation of motion what it is, d2x dt2 equal to minus y squared, omega squared x, shows a symmetry under x going to minus x. The structure that we see in the solution is partly connected with this symmetry. I said partly because the other parts come from the minus sign, which has to do with the restoring character of the force, and partly due to the fact that it is x squared. Had it been x4, this symmetry x2 minus x would have been valid. However, you wouldn't see exactly the same structure because of some additional features if we have to really understand the solution, but I'm not going into that. But the lesson we learn is that the trajectory that we see in the simple harmonic motion is related to a particular symmetry of the problem. And even without going to anything exceptional, you can see one very visible thing which is the consequence of this potential, which is that the trajectory of the oscillating bob does not depend on whether the pendulum starts swinging from the left or from the right hand side. Left and right difference between lefts and rights has been obliterated by the potential itself. And the detailed structure is partly responsible for the potential, but the structure of this thing is partly controlled by the potential and partly by a few other physical aspects of the motion. So what we see is that symmetry is not, I deliberately chose this example where symmetry is guiding or relating to some aspects of the solution to the problem, but at the same time making us conscious that thinking of symmetry, we must not forget the physical reality in all its ramifications. Next slide. Things as simple as Newton's law also shows this. Consider one-dimensional motion given by this example which we have studied in our high school. V being the potential whose gradient decides a force. Now, if x, that is to say, space coordinates shift by a constant amount a, naturally v is v still, because it's not v is going to v, dv dx is unchanged. So dv dx does not change, and therefore the momentum of the particle. Sorry, I probably didn't say it clearly. I am talking about a situation where under any shift in coordinates, x going to x plus a, v is unchanged. That is to say, a situation of constant potential. This can be related to translational symmetry of space because things don't change under translation. In this case, dv dx is 0, and therefore the momentum of the particle turns out to be constant, thus relating momentum conservation principle with the homogeneity of space, that is to say, unchangeability of everything if you move about in space by fixed translations. This is a symmetry, and when a particular dynamical system exhibits some symmetries like this, that system conserves momentum. So it is translational invariance that we are talking about as a symmetry. Next slide. Newton's laws have some symmetry. In 3 dimensions, if we write the laws in the form in the second line of the slide, where the force is some function of position, you can see it is true in other cases also, but let's consider this case. The law is symmetric under time reversal. T going to minus T will not change anything. Let us remember this and come back to it later in our talk. And in the meantime, also note that when an object is moving under a central force, which is dependent on radial distance only but not on directions, this is a kind of spherical symmetry of a problem. There is a symmetry under rotation in space, and with that is related to the conservation of angular momentum. So momentum conservations, angular momentum conservations, and also although I'm not explicitly discussing it, energy conservations, these are the results of certain symmetries related to space and time in a particular physical problem. And although I'm describing this in terms of just high school mechanics, these have far-reaching consequences in the very important recent formulations of theoretical physics as well. Next slide. Please load down to all the way. Consider some easy thing, a point charge and its Coulombic electric field due to it. Now, even before we know what the origin of it, that an isolated point charge will have its electric field along the radial direction connecting the point charge to the point at which you measure the field, that we can say even without looking at anything else. Why? Because the field must have some direction. And with respect to the point charge, at a point there is no other conceivable physical direction preferred compared to others. The only direction which nature has chosen for this kind of a setup is the radial direction from the origin, that is to say the point charge location, and the point at which you are measuring the field. Thus, the spherical symmetry of the problem told us, even without anything, that the electric field is like this. That the field on top of this is an inverse square field comes out of Gauss's law, and this proof I am not giving. But one thing I am just reminding everybody, from this E dot ds equal to this, in order to arrive at the result in the last line, you assumed something, that the Gaussian surface is spherical and E and ds are parallel to each other. Who told us to start with that E dot ds will have an angle 0 between E and ds? That is because there is again this spherical symmetry which has sort of become part of our breathing process here, and even without justifying it, we step on to say that E dot ds should be E times 4 pi r square. So these are examples where symmetry, even unconsciously we end up using, but such symmetries, spherical symmetries of problems sometimes have very, very important consequences, like we see in many things involving the Coulombic force, hydrogen-like atoms and their quantum mechanics, in problems related to gravitation, and a lot of other things. Next slide. Again, I come back to the ammonia molecule. We remember this structure and go over to the next slide. Please slide down. The nitrogen and hydrogen atoms, they generate certain electrostatic potentials. Electrostatic force, by definition, when it is between two charges, they have a radial character, and for one particular charge, they have Coulombic character. But the proximity of nitrogen and hydrogen atoms cause polarization in the atoms themselves, and certain dipoles and even higher poles are created within the atoms. So starting from a spherically symmetric structure, you have a complicated electrostatic potential depending on spatial orientations and distances, governing the location of the nitrogen atoms or the 3 hydrogen atoms with respect to the nitrogen atom, and the final stable structure will correspond to the minimum potential energy answering to the electrostatic structure or electrostatic interaction, which at the root is spherically symmetric or Coulombic in character. The covalent bonds binding the 3 hydrogen atoms to the nitrogen atom develop directionalities as a result of this. So what we are observing here is that there may be at the very root a spherical symmetry of Coulombic interactions of a point charge, but when a complicated system is assembled with several charged objects, the very character of the assembly leads to a stable electrostatically governed structure with a symmetry very different from spherical symmetry. So this can be really intriguing, and deriving these steps are the objects, is the objective of theoretical physicists who are engaged in such pursuits. In the next example, in the next slide, we see again the sodium chloride structure. I have already spoken about the symmetry under translation by fixed lengths, which maps one chlorine to another and so on, and the structure remains invariant in the process. Please go to the next slide. Roll down, Again, there is a symmetry under space translation over specific distances. An electron, as a result of this symmetry and this kind of structure as a whole, experience an electrostatic force or an electrostatic potential in this system, which is very different from what it would have observed in a single sodium atom if all that we had was the atom and the electron was the outermost electron. Therefore, the energy levels, when we solve the corresponding quantum mechanical problem, the energy levels for such an electron will be very different from those, for example, in a hydrogen atom, as predicted, for example, in Bohr's atomic model, and which is corroborated by detailed quantum mechanical calculations. These energy levels are actually packets of continuous energy levels punched into bands. So several energy ranges are where electrons can have their energies in a structure like this, and these energy ranges are often separated from each other from non-allowed energy values. So these are the so-called energy bands, and studying the band structure of various materials is a sub-brand of physics or a branch of physics itself. But one has to remember that the existence of such bands and the guiding principles in the formations of band is the translational symmetry of the lattice structure which I have spoken about. Of course, in reality, there are deviations from these crystalline structures, something which is quasi-crystalline. They have their own symmetries, which are kind of reflected on much larger length scale, and their intervention in certain solids make the available energies even more different, even more varied, and even more interesting physically. Next slide. Now we come to the submicroscopic world related to light. Back. Although light has wave property, we also know that it has corpuscular property also, as was first kind of effectively used in photoelectric effect by Einstein. And these packets or corpuscles of light are called photons. Suppose we have a box, perfectly reflecting box, where we have photons with various energies running around. Now, various energies means various frequencies, because A equal to h nu for a photon. So there is a distribution of energies. Suppose a certain temperature is assigned and these photons are treated like gas molecules. Then what will be the number of photons of what energy, in other words, what frequency, at a given temperature, shows the energy distribution of photons, very similar to the Maxwellian distributions in ordinary ideal gases, where also the distribution can be expressed not in terms of velocity, but in terms of energy of the gas molecules. Now, if assuming that the same calculational mechanism that was responsible for yielding the Maxwell-like distribution, if we use that and try to find how many photons will be seen with energy between E and E plus dE at temperature T, if we calculate it like we did for gas molecules, the answer will be simply wrong. They would not agree with experiments. So this led to a puzzle, and the reason was found to be the following. Next slide. Yes, back. The reason is that the simple-minded calculation equating photons to well-known gas molecules, that neglects the symmetry of the quantum world, and we must go to the quantum world to understand the behavior of photons. The thing is that if there is a photon with a frequency mu1 and a photon 2 with frequency mu2, then what is called the quantum mechanical wave function of these two photon system will tell you that 1 and 2 will not change anything in reality or in observation. That is to say, photon 1 with frequency nu1 and photon 2 with frequency nu2 as a quantum system is perfectly equivalent to photon 1 with frequency nu2 and photon nu2 with frequency nu1. And this kind of symmetry respects visibly, which is called exchange symmetry, reflects visibly in the derivation in the quantum formalism of the energy distribution of photons. And following this kind of a methodology and keeping this symmetry in mind, the correct energy distribution, which is called the Planckian distribution, was derived for photons, treating them as particles. And the credit for that goes to Satyendranath Bose. This was a celebrated work called Bose statistics. But the departure from Maxwell-Boltzmann statistics, which created a new branch called quantum statistics, which was Bose's fundamental contribution, is based on this indistinguishability of quantum particles, which in other words is the reflection of a symmetry in the quantum world, the way I have described it. Next slide. Having spoken about symmetry, by the way, I hope you have told the participants that I am stranded outside Calcutta and sometimes electric connection goes away in the building where I'm staying. The generator takes over immediately, but the internet router takes a while to come up. So in that case, I request people to wait for 5 to 10 minutes. Anyway, let's hope that will not happen, but it can happen anytime. And it will happen when the power comes back again. Now, consider a projectile, a basketball thrown into a basket. This is projectile and neglect air friction. Now, this motion is guided by Newton's law. Suppose you videograph this basketball and go to the next slide. The onward motion is dictated by Newton's law, and the onward motion, the Newton's law, the force it uses is gravitational force. So, remembering the equation of motion we discussed, Newton's law has a time reversal symmetry. Now, if we now run the video backward, the reverse motion, when the ball runs out of the basket, assuming somebody is pushing it, as if somebody is pushing it, and comes back to the hand of the thrower, that will describe a parabolic path, which is also perfectly according to Newtonian mechanics. That means pure Newtonian mechanics has time reversal symmetry, reflected not in a structure, but a trajectory this time. There is no violation of Newtonian mechanics by running the video backward. So, this is a story of a symmetry we are talking about. But now, since I talk about symmetry is broken, we first start by remember that the same is not true if air friction is considered. Because some energy lost in the onward motion is sort of regained if you run the video backward, and the detailed kinematics consequent from this will not be following the usual expectations, because the energy converted into heat through friction will not be recovered in reality. This immediately suggests that certain symmetries in nature are broken. Now let's go to the next slide and take a more concrete example. Let's put a hot and a cold body in contact. Attach a thermometer to it and turn a video camera on. After a while, the thermometer readings, one will come down and the other will go up till the temperatures equate. This follows from elementary calorimetry. So this is the law of thermal physics as dictated by experiments. Now if you run the video backwards, what will you see? What you will see is not following the laws of heat transfers. Two objects in contact, one is becoming hotter and hotter and the other is being colder and colder, and nothing else is allowed to interfere with the system. Therefore, the lesson we learned from this is something that was hinted when I mentioned friction in the previous slide, and the lesson is that the laws governing thermal phenomena have no time reversal symmetry. So the story of nature is not 100% the story of symmetries. It is also partially the story of symmetries broken. So this is what I started by emphasizing. And let us now talk about, we have spoken about symmetries unbroken. We have spoken about symmetries broken. And let us now go to the world of elementary particles. Next slide. Where the remaining part of the talk, I'll talk about symmetries unbroken as well as symmetry broken. Elementary particles known so far essentially are the elementary constituents of nature, or everything in the universe have the particles listed in the tables as their constituents. This includes permanent or long-lived particles like our bodies and everything, the earth, and also very transient and short-lived objects, some particles which are created in nuclear reactions or particle accelerators, but decay within a picosecond and so on. They are also seen to be constituted of many elementary particles, but the entire set of such stable or unstable objects seen in nature have been reduced to constituents listed in the table here. There are 6 quarks, up, down, charm, strange, top, bottom, 3 what are called leptons, electrons, muons, and taus, and 3 neutrinos, and 4 force carriers, photon, gluon, Z, and W. All the phenomena related to elementary particles seen so far are governed by these particles, and they are the constituents of all that we have seen, stable or unstable in the universe so far. On top of that, a spinless particle, the particle having no intrinsic angular momenta of its own, all the particles here above have angular momenta. The building blocks in red and green, quarks and leptons have spin half. Their angular momentum is half h cross. And the force carriers have angular momentum 1 times h. But on top of that, a spinless particle, which has a crucial role about which we'll speak towards the end, is also found in nature, which is called the Higgs boson. Whether it is the Higgs boson or a Higgs boson is a debate into which I'm not entering. So these particles on the table and the Higgs boson, and the Higgs boson constitute what are called material particles, and the particles which serve as carriers of fundamental forces. What are the fundamental forces? Let's go to the next slide. We know about several fundamental forces. One of them is electromagnetic things, interaction, without which we could not have been able to participate in this seminar today. Next, gravitational interactions, from which there is no escape from any of us. These are 2 interactions that manifest themselves at the macroscopic or observable level, but there are 2 more interactions which participate in microscopic or submicroscopic levels. Next is, slide. Next slide. The strong force which is responsible for, next Please go back. Strong force, which is responsible for what? Holding quarks together in protons and protons and neutrons together within the very small length of the nucleus and so on. This is called the strong force. And next slide, the weak force, which is responsible for certain phenomena, actually a very rich collection of phenomena, the easiest example of which is beta decay in nuclei, with which we are all familiar. Now go to the next slide, please. Bus. Now, if based on the particle zoo I displayed in the table in 2 slides back, table 2 slides back, and the, not 2 actually, 5 slides back, and the 4 fundamental forces which we showed in the last 4 slides, we have to find out the theoretical laws describing the effects of these interactions, but these laws will have to be quantum theories because we are talking about ultra small distances. Typically, we have gone down to the distance scales of 10 to the minus 8 or 10 to the minus 10 meters. Sorry, 10 to the minus 18 meters. I was unmindful. This is the problem of not looking at an audience. You tend to doze off. 10 to the minus 18 meters is the distance we have reached so far in experiments, and laws have to be controlled by quantum theory there. I have conveniently left out gravitational force in my table. That is because up to the length scale, or rather down to the length scale we have reached so far, gravitation is a very, very subdominant effect. In order to see the effect of gravitation, you have gone to 10 to the minus 32 meters or smaller lengths, but no experimental facility so far allows us to probe such lengths. And therefore, there are lots of uncertainties about what happens there. As a consequence, the quantum laws of gravitation are also not formulated satisfactorily so far, although efforts are on. Now, for the remaining 3 interactions, let us talk now about them. Electromagnetic, weak and strong. We won't talk about all of them. Let's talk about electromagnetism first. Think of only some electrons and photons and so on, and let us think in terms of electromagnetic interactions, but what I am saying will be true for other interactions as well. Now, if we take a collection of particles, elementary particles in the universe, and think for a moment that nothing changes if everything is rotated by the same amount. That is to say, a global rotation in 3 dimensions is given to the huge, almost infinite assemblage of elementary particles there. Since all directions in space are ultimately equivalent, does it mean any change? It doesn't. So that means there should be some symmetry in the quantum laws involving these elementary particles. For a moment, we think they are not interacting. They are all free standalone particles. Even there should be a quantum law. And these quantum laws, which will describe their behavior, they will show the effect of a rotation which is global, same for everything, because in space, nothing changes as a result. Now, that is rather easy to conceive. Now, suppose we become greedier. We suppose or we demand that a different degree of rotation is given to the elementary particles at different points. And still we demand that the physics should not change. This probably is asking for too much, we will say. That point 1, I give all physical quantities related to an electron in point 1 in space at particular rotation, and positrons at some other point, all relevant physical quantities will be given rotation by a different amount. And then we are demanding that things will not change. Outlandish as such claim may be, it tells you that that even may be possible, because suppose when you give a rotation at one point, another particle at a different point is alerted to it so that it adjusts its relevant physical quantities accordingly so that the net effect of 2 particles is same everywhere. Then such a local rotation at each point also may keep the system invariant as far as physical properties are concerned. But what does it imply? Implies that there must be some causal connection or a way of communication between 2 points where I am giving such rotations. That is to say, such a local symmetry or local rotational symmetry, even that is conceivable, but then invariably there must not be particles alone in nature, but a way of their mutual communication. In other words, signals, in other words, interactions with force mediators. In fact, it is in this way that the photon may be looked upon as emerging from a set of free electrons and their quantum theories. And that's how the quantum law of electromagnetism, namely quantum electrodynamics, which is the so-called quantum field theory, relativistic quantum field theory, that theory has emerged as one of the most well-tested, most consistent quantum theories in nature. And the laws of interactions it predicts is not seen to be violated in any experiment so far. And all the theoretical inconsistencies that could have arisen in such a theory are taken care of rather remarkably thanks to this kind of local rotational invariance. Next slide. Now, people were again greedy. Scientists are a greedy lot. When some theory succeeds, the next theory they wanted to build in the light of what they have already learned or in the shadow of these kinds of theories. Of course, they face disillusionments, they have to change their way, but they nevertheless try this. So the first quantum theory of elementary particles developed was for electromagnetic interactions, namely quantum electrodynamics. And as I've already said, this was a highly satisfactory theory. Now, as I've already seen, or rather mentioned, many of the good features of this theory are seen to be based on, or rather connected with, the symmetry I just spoke about. This kind of an invariance that local rotations at different points do not change, provide the interaction mediator comes into the picture and participates in interactions in such a way that the effects of rotation at one point are adjusted at another point through causal signals. When people were building a quantum theory of nature, a quantum theory of weak interactions, the force, for example, responsible for beta decays, but responsible for many other things also, a similar attempt was made that a similar symmetry would work there also. Take an example like a neutron going to a proton, an electron, and a neutrino and an antineutrino. At the quark level, remembering the quark constitution of neutrons and protons, it amounts to a so-called down quark decaying into an up quark, an electron, and electronic antineutrino. Next slide, please. But, as the last line said, that is not enough. Okay. Weak interaction has an additional feature over and above electromagnetism. And this time it is not a symmetry, but a symmetry broken. So we are building a theory based on symmetry, taking a cue from electromagnetism, but we have to think of such symmetry which is broken in weak interaction. In neutron going to proton, electron, and antineutrino, the symmetry, not symmetry, there is one very important feature observed. The electron that it emerges has always its angular momentum, or rather spin orientation, corresponding to that of a left-handed corkscrew. That is to say, the spin is the intrinsic angular momentum of an electron, which reflects itself in its response to a magnetic field. But the electrons here, the electrons emerging from beta decay, if you take their projection, the projection of their angular momentum along the direction of motion, that will always corresponds to the direction of rotation or sense of rotation of a left-handed corkscrew. That's surprising. Who told us that left is chosen over the right? That was never the case in electromagnetic processes. So therefore, seeing repeated manifestation of this phenomenon as well as many others related to weak interactions, people were forced to the conclusion that weak interactions make a distinction between left and right. The symmetry between left and right is thus broken. This symmetry is given the name parity. So weak interaction is parity violating. Well, a symmetry broken is fine, but this broken symmetry brought with itself another challenge for us. When you demand a quantum theory of weak interactions in the fashion of quantum electrodynamics, or demand a symmetry of similar kinds, and at the same time incorporate the input of parity violation in the theory, that is to say, make the theory of such form which violates parity, then, next slide. No, just a minute. Then you see something striking. These are inconsistent in the basic level. Demand of a symmetry like in quantum electrodynamics is unbroken, and explaining parity violation at the same time are mutually consistent only if all material particles are completely massless. No massive particle is there. But that's a big shock. Next slide. Bus. Now, we know there are electrons which have masses. We know there are muons which have masses. We know there are quarks which have masses. Now we want to have a theory of their interaction, and just because there is this weird phenomenon called left-right symmetry or parity broken, the beautiful theory of electrodynamics cannot be extrapolated to weak interaction, because that would mean that all particles are massless. Ridiculous. Not only ridiculous, that's a big challenge. But the challenge was overcome with another very weird hypothesis, which was shown to be experimentally verified. The hypothesis is that all particles are massless to start with. And there is, on top of the particles which I listed in my table, there is an additional particle which has no spin or intrinsic angular momentum, which has no electric charge. And after one of the proposers of this was called the Higgs boson. This was attributed with a very strange property, namely that it leaves some energy all over the vacuum. In quantum mechanics, you know, this is a quantum theory, this is possible. A harmonic oscillator has a 0-point energy. This vacuum energy is kind of a 0-point energy, which Higgs bosons are leaving all over the vacuum. There are twofold consequences of this. First of all, Higgs boson leaving its energy, part of the energy with the vacuum, means vacuum inherits something from the Higgs boson. That way, it does not treat all particles on the same footing. It's just like in today's political world, people for doing all sorts of malpractices manage to bribe certain politicians and are treated differentially everywhere. All classes of politicians do that. Here, the vacuum inherited some properties of the Higgs boson as bribe, and therefore the Higgs boson gets a preferential treatment in something or other. As a consequence, the symmetry which was intrinsic to the system is broken in a certain sense if you look at it not from the angle of the particles and their interactions, but from the angle of the vacuum. The second most important observation is that once the symmetry is loaded with vacuum remnants, once the vacuum is loaded with remnants of the Higgs boson, the vacuum is loaded with the remnants of the Higgs boson, then all hitherto massless particles have to push through vacuum, and they develop an extra inertia, and they look massive in the process. Because more massive means I have more inertia. If a room is empty, I can walk freely from one end to the other. If it has knee-deep water, I have to walk slowly. I am slowed down, and to an outsider, it seems I am more massive than I originally was, and that's why I am slowed down. So therefore, this vacuum remnant or vacuum legacy inherited from the Higgs boson makes the vacuum of such character that particles which are in essence massless are developing masses by pushing through the load of Higgs remnants in the vacuum. And any particle which moves, has stronger interaction with the Higgs boson in the underlying theory, will have to face stronger resistance of the vacuum remnant and will appear more massive. Just like instead of knee-deep water, if I have knee-deep honey, I will appear more massive because the viscous force is more. And the exception here is the photon, because photon couples only to charged particles. It doesn't couple to neutral particles. And the Higgs boson was to start with a neutral particle, and its vacuum remnants are also neutral particles. So the force photon does not have any interaction with the vacuum remnants of the Higgs boson, and therefore the photon remains merely massless as we see them. So here we keep all ends, and if your theory is formulated in this fashion, you can see that you really have the original symmetry intact in a particular sense, but at the vacuum level, because of this effect we have just spoken about, the symmetry is apparently broken or hidden, gets hidden, and a theory whose kind of relevant terms in the theory are written down with reference to such a vacuum, which is sort of asymmetric thanks to the Higgs boson, you can see clear manifestation of the mass terms for particles consistently with the violation of parity without causing any problem there. So this way, the Higgs boson killed several nuisances with a single stroke, and at the same time, not only paved the path towards an explanation of whatever we were seeing, but also introduced in the world of elementary particle the possible existence of a new elementary particle anticipated from an angle very different from whatever was the reason for anticipation of other particles. It was a very novel anticipation of a particle, which people might even have thought very artificial. Please, next slide. The way particles acquire mass can be seen like this. Through consider a crowded room with particles sitting all around, and a dignitary enters from one side of the room. She immediately gets several people crowded around her, starting from journalists to sycophants, who form a cluster around her. And as she is moving across the room, these people are also moving around. So, to a person looking from afar, the otherwise thin person, probably this lady was very thin to start with, she looks whatever you find her to be. So, mass acquired through interaction with the remnants in the vacuum of the room, which is the vacuum with so much of a crowd. So, this is an underlying principle as shown in this cartoon. But let's go to the next slide. I'm almost at the end of my talk. This particle was conceived of in a very strange manner, very, very unnatural, counterintuitive, unusual manner. And people were not even true whether we are talking about a real particle in nature. The point is that even before it was seen, various experimental examples or observations were gradually making us more and more convinced that this particle is indeed there. But it took us about 50 years since the proposal to actually see such a particle in the experiment called Large Hadron Collider at Geneva. The discovery came in 2012. So, with this discovery, the particle zoo I indicated in one of the earlier slides got completed, and pieces of the jigsaw puzzle seem to fit in. So the game of symmetry and broken symmetry thus went on to bring us to the point where we stand now in the world of elementary particles. Next slide. Bus. Now, I'm in my last but one slide now, and I think I have kept myself to the time schedule well. So we are inheriting some wisdom in there, because the elementary particle world, like a lot of the macroscopic world and the quantum mechanical world has been dictated by considerations of symmetries and broken symmetries as well. Now, this is not the subject of my discussion today. There are reasons to think that there are more than what meets the eye. That is to say, in the elementary particle world also, the existing theory is not complete. It has certain incompletenesses, certain features which are unsatisfactory, and there are certain observations which still requires the addition or supplementation or extension of the existing theory of elementary particles. And so, based on what we told you just now over the last 1 hour, one has reasons to think that there are perhaps yet undiscovered symmetries in nature. And if we use the wisdom we have just gained, probably there exist not only additional symmetries, but also additional symmetries which are broken, but broken with a pattern. That is to say, there is a method in the madness of nature. So one may argue as to whether the Higgs boson, which is a manifestation of such method in madness, could still indicate the existence of more physics than we know, and could there be more evidences of Higgs-like phenomena leading to a richer world of elementary particles. Last slide. Of course, this is a matter of speculation, but as I have already told you, there are several dissatisfactions with the existing structure of elementary particle world, and therefore expectations are piling up like anything. But as I have mentioned already, the last word, just like the first word in physics, will come from experiment and observation and extreme finesse in observation, because the Higgs boson discovery, for example, its proposal, its properties, and its theoretical impact, those were matters of fine theory. But in actually seeing the Higgs boson, the incredible effort that went on at Geneva to isolate one meaningful event in high energy particle collision out of maybe 10 to the power 12 meaningless events, this required an incredible effort, and the experimentalists who achieved this, my hats are just off to them, and they are no less, probably much more deep, intricate, and skilled in unfolding nature to us. So we end with the lesson that the story of symmetries and symmetry broken are part of nature, part of the way laws of physics are formulated, and we anticipated much more. But the verification of such very, very strange and very, very subtle principles, even in the most abstract theory, the verification arises out of sophisticated technology, concrete data, and backbreaking experimental work. Not only backbreaking, extremely wonderfully creative experimental work. With this, I finish my talk. Thank you very much. I have finished exactly in 1 hour. Thank you.
Thank you, sir. Thank you, sir, for your very interesting and lucid talk. We have got a gross idea about the role of symmetry in physics. The symmetry, what is the comparison between a symmetry and antisymmetry, and the symmetry, role of symmetry in the elementary laws of nature, and many other things in the quantum laws, in quantum electrodynamics. Everything we have get a gross total idea about symmetry. Thank you again for the relevant talk.
Thank you.
Now the session is open for the question answer, and I just request Dr. Aditi Dash and Dr. Parikshit Datta of the Department of Physics to conduct the question answer session. Parikshit and Aditi.
Okay. Thank you, sir.
I can already, just a second, I can already see some questions in the chat box. Shall I start by answering them?
Yeah, if you want to, then please.
At least let the first few that I see, I answer, I can see them. There is a question from Shakshi Tyagi. She asks, do antiparticles follow up symmetry? The answer is yes. In fact, as far as these various symmetries in the world of elementary particles are concerned. Many of them, if followed by particles, will be followed by antiparticles as well. In fact, this is an interesting thing. Particle antiparticle symmetry, just like left right symmetry or parity, is another deep symmetry of nature. As far as electromagnetism is concerned, this symmetry is very much there. That is to say, electrons replaced by positrons everywhere will keep the laws of Maxwell's in the classical electrodynamics and the laws of quantum electrodynamics in its quantum version. They keep their remaining unchanged if particles are replaced by antiparticles. So this symmetry is called charge conjugation symmetry, and it is obeyed by electrodynamics. However, when you come to weak interaction, I didn't tell you so, but our friend kind of provoked me to say so. Just like parity or the symmetry between left and right is broken, so is broken the symmetry between particles and antiparticles. Particles may have symmetries of their own, antiparticles may have, but the phenomena related to weak interactions or weak decay don't put particles and antiparticles behave in identical manners. So weak interaction violates not only parity, but also the symmetry between particles and antiparticles, or charge conjugation symmetry is broken. So this is the answer to your question. So if I look at questions, I can see one question. Please mention briefly the symmetry scenario beyond the standard model. That is too much to describe here at the fag end of the day. The standard model basically is a quantum theory of weak, strong, and electromagnetic interactions all together, and each of them is governed by a symmetry, which is a continuous symmetry in each case. And this continuous symmetry is like the symmetry of a circle that I showed in my very early part of the talk, where you can have a rotation to any degree with continuously varied values of the rotational angles. So such symmetries, operations form groups, and there are various kinds of continuous groups which underlie the theory of the three interactions. For weak interactions, this is a group called weak and electromagnetic interactions taken together. This is a group called SU2 cross U1. And for strong interactions, there is a group called SU3, a combined operation under which the operations follow this group property constitute the underlying symmetries of the standard model. It is impossible to do more justice, because then one requires several hours to gradually build to the concept of these symmetries.
Sir, I think there's an interesting question here also.
Achha, which one is?
So the Higgs boson explains only 0.1% of the observable mass. Do you think there are other candidates which lie undiscovered theoretically and experimentally? So the last question.
Yes, I'm answering that. The a priori answer is yes. Because, for example, just like the electron and the muon and the tau, if there are more particles of the similar nature, then we may not have seen, maybe they are so heavy that we are not seeing them or something like that. Then the masses of these particles will also arise out of the Higgs boson in the same way that they have arisen in the theory I have described. However, it may be that there are other particles which acquire their symmetries from other Higgs-like particles which we are not seeing them yet. When people are trying to go beyond the existing theory, people are using some such properties, some such theoretical structures, where arise other particles, which will probably require the existence of other particles, either similar or slightly dissimilar, but broadly similar to the Higgs boson, to which their masses may owe themselves. But there was some 0.1 something.
So there he's
no. This statement is not correct.
0.1%.
No. This is not a correct statement. It's not sure that Higgs boson explains 0.1% of the observable mass. All of the observable mass is explained in terms of the Higgs boson. Is the answer? The observable mass is less than 5% of the total mass in the universe, and there is some dark matter or missing mass. That's a different statement. The question has slightly confused between these two statements. The observable mass so far is all explained excellently by the Higgs boson.
Okay. Thank you, sir.
Okay.
So I
What is
think
the other question? By
I think
breaking symmetry, can we remove the degeneracy? This is not. No. Yes. In quantum mechanics, many of these symmetries that we think of are responsible for the degeneracies, but always the symmetries are not so obvious. For example, in a hydrogen atom, whose quantum theory is studied in the second or third year of BSc, there are conserved so-called quantum numbers like the magnetic quantum number and so on. Some of them are results of symmetries that we know, like energy conservation, angular momentum conservation, which are results of symmetries. But for example, this L quantum number, which decides the orbitals, so 2s, 2p, these kinds of things, s and p have different values of L. When you break the degeneracy, you have to apply something and see the degeneracy broken. But this degeneracy of s and p orbitals in a hydrogen atom, let's say, this prima facie is not the result of any symmetry that are commonly looked like translational invariance or spherical symmetry or anything, the time independence of the Hamiltonian. That can be traced back. The L quantum number and the degeneracy and the symmetry responsible for it can be traced back to a very strange kind of vector that you can construct for a particle which is moving under the inverse square interaction. Coulomb force is an inverse square force, we know. And this vector is called the Runge length vector. Runge length vector. And the fact that this vector is not changing with time for a particle moving in an electromagnetic field, this fact, you have to do some mathematics to do it, not necessarily in quantum mechanics. If you are studying Keplerian motion, you can do some calculation and find it out. This Runge length vector, that it does not change with time. The vector constructed is, if you call it L, dl dt is 0 for this vector, wherever the rotating particle is. That corresponds to, for example, for a Keplerian orbit, the non-rotating character of the tip or the perihelion of the orbit, spherical orbit, not spherical, elliptical orbit. So this kind of an symmetry, which is rather hidden and intricate in a case like the hydrogen atom, is responsible for some degeneracy, which is not obviously meeting the eye. So in order to break this symmetry, you have to create a situation where this Runge length vector is no longer there as a constant.
okay, thank you, sir.
And I don't know.
One question, sir.
Shivesh has a
Okay.
question, sir.
Okay,
Reverse
maybe
symmetry.
you can read out questions because I'm losing tracks of them.
Yeah,
So
sir.
in-
So Shivesh
Projalo-
Paramanik has a question. Sir, please tell us about flavor symmetry in meson octet and baryon octet. How the symmetry arise?
Unfortunately, I cannot enter the discussion. Flavor symmetry is an approximate symmetry of nature, where in some approximation all quarks are found to be of comparable mass. In practice, there is a large breakdown in that symmetry, and this symmetry arose as a result of some hypothesized symmetry in the initially proposed theories of strong interaction. These theories were not found to be totally satisfactory. They have been replaced later in favor of more effective theories where symmetries arise in different ways. And whatever we can say about flavor and the non-degeneracy or inequality of the masses of various quarks are not in contradiction with those theories. So this is the theory of strong interaction. This kind of octet and flavor symmetry and near degeneracy resulting from that, these are matters of history as parts of physical theories which have been by and large discarded, but which are illustrating in telling people how our understanding gradually evolved. That's all.
Okay.
One question,
Thank
sir.
you,
Our ex-student Prajalok Chattopadhyay has asking to
Uh-huh.
explain the Noether's theorem. Noether's theorem.
Noether's theorem says that for any continuous symmetry, there is a conserved current. That doesn't mean anything to anybody. For example, if you take a particle moving in space where there is translational invariance, like I told you, that is to say, the that is to say, the x going to x plus a doesn't change anything. As I told you, in such cases, momentum is conserved. So this was a continuous symmetry. X going to x plus a could take any value from 0 to infinity continuously. Now, under this, the system wouldn't change anything. As a result, we saw in a very elementary example, the momentum is not changing with time. Now, stretch your imagination and think of momentum as a electric-like charge characteristic of the particle. Now, a charge conserved means what? When electric currents are moving into a particular region in space and some currents are moving out, then this current is conserved means whatever current is coming in is going out through exit paths as well. And then within that volume, the electric charge remains constant. So for every, Noether's theorem says, for every continuous symmetry like the one I spoke about, there is a conserved electric current of this kind. And for every conserved electric current, like I told you, some current is coming into a volume of space, then some current has to go out. And if that happens, in that case, the charge contained in that volume is unchanged. Now you extrapolate the idea of charge and map it to the momentum of an object, and the momentum is unchanged in this particular example. The reason behind being a symmetry of the theory, namely translational invariance. So momentum is related to the Noether charge of the continuous symmetry of translation. I mean, a deeper and more elaborate description of Noether theorem is beyond the scope of the present discussion.
Okay.
One question asked is the Higgs boson responsible for gravitation? Of course it is. Anything that has mass, Higgs boson has mass of its own, and anything that has mass is responsible for gravitation. But if you mean it is a gravitating object, just like you and me are, just like protons and neutrons are, just like electrons and quarks are, a Higgs boson is also responsible for gravitational force. But if by asking this question you mean, does the Higgs boson mediate gravitational interaction, then of course the answer is no. No.
Sir, okay, so one question.
Now I am losing track.
Yeah, so one question from YouTube was, what determines whether a particle will have spin or not?
Nobody knows.
Satyam Das. So nobody knows.
Particles have been seen with various spins. What decides that the electron is spin 1, whereas the photon is spin half, nobody knows. All we can say is that the matter particles we have seen at the fundamental level so far are mostly spin half, excepting the Higgs boson, which is spinless. And all the force mediator particles are spin 1 so far. But why an electron also could not be a spinless particle to start with in nature, in which case its properties would have been very different. Unfortunately, that is not known from a still deeper principle. And all we can say is that we have been handed out these particles, and these behaviors of these particles are explained rather well in terms of the description we are used to. And somebody says something about supersymmetry.
Yeah, I think.
Well, that is again opening another Pandora's box. I'm not going into it. Some very fond thinking by particle physicists over many years, and I unfortunately happen to be one of them, have toyed with the idea. There are some definite motivations of that. I'm not going into that. That there are two kinds of quantum particles in nature, bosons and fermions. Spin half and spin 3/2. Half integral spin particles are fermions. They follow Fermi-Dirac statistics in their large-scale behavior, whereas integral spin particles like spin 0, spin 1, etc., they form Bose-Einstein statistics. They follow in their collective behavior, like I illustrated in the example of the photons and when I described S.N. Bose's work. Now, there have been some fond expectation that some symmetry lies in nature, maybe we haven't seen it so far, between bosons and fermions. So, in some way, in the theory, if you replace bosons by fermions and fermions by bosons, interchange them in a mathematically admissible manner, the physical laws will not change. This is extremely appealing. Theories have been constructed, and there are some experimental motivations of that so far, but not a compelling motivation as yet. And unfortunately, people have formed a lot of predictions of what could be seen in nature if there was this symmetry called supersymmetry. Unfortunately, none of the predictions have been verified so far. This does not mean that we won't look for it and it is wrong. But after some 50 years of effort or more than that, people have not yet seen supersymmetry. Again, there are perfectly understandable reasons for this. So whether supersymmetry is actually there or not is very much an open question or undecided issue.
Okay. So one interesting question from Shujoy Shaha is why there is more particle than antiparticle in nature.
Again, an undecided question. First of all, how do we know, let us say, the how the universe evolved, of course, has its own theories. The most popular theory of this area relating to the structure of the universe or evolution of the universe is called cosmology. And the most popular theory in cosmology is the so-called Big Bang theory. I'm not going into details of that, but all it tells us is that it all started from one point in space and one point in time, beyond which we cannot go back because space, time, and any physically relevant quantity was not of an meaningful value beyond this point. So, Big Bang, in a way, in a somewhat inexplicable way, marks the beginning of the universe. Now, if our common expectations have to be relied on, then you would expect that Big Bang started with as many particles as antiparticles, because at the Big Bang level, no interaction caused anything. Out of nothing or something that we don't understand is a better idea. Particles and antiparticles and so many other things were created alike. Then, as the universe evolved, we see that we have come to a point where there is a clear disparity. Because, for example, we are all built of electrons, protons, and neutrons. Because we are yet to get any indication about any corner of the universe, and now astronomers and astrophysicists have done a pretty exhaustive and remarkable job. Then over the entire region of the universe explored so far, there is nothing built with positrons, antiprotons, and antineutrons in the same manner. So overwhelmingly, particles dominate over antiparticles, or matter dominates over antimatter in the universe. This problem is given a technical name of baryon asymmetry because overwhelming part of the massive component from particles comes from baryons, a class of the most popular class of baryons being protons, as compared to antiprotons. So how such a disparity between particles and antiparticles, or matter or antimatters, could have been created in the universe starting from a perfectly equitable distributions at the Big Bang. Even that is a fond expectation. But if at all there was an equitable component of each, then how could this distinction come is something again that people don't know. Because this is one of the very important unsolved problems, and this is something that astroparticle or cosmoparticle physicists are working very hard to find out, but unfortunately no satisfactory explanations have come in yet. It is one of the most important unsolved problems of particle physics.
Okay, sir. So more questions. One question was, what determines how strongly a particle interacts with Higgs boson?
What determines? Then you have to go to the quantum theory. There is an interaction term which decides the coupling of the Higgs boson to a particle. All you can say is that the stronger is this interaction term, Higgs boson coupling, the higher is the mass the particle develops in the process. And for that, I give you an explanation also. Namely, if you are in a room with knee-deep water, you will develop some mass or some inertia in wading through knee-deep water. But if you walk in a room with knee-deep honey in a room, then you have to push much harder and they will be slowed down much more and you will be seen more inertial or more massive. So, the fact that we see particles with various masses in nature basically tells us that various particles that we have seen so far have varied strengths of interactions from Higgs bosons. These different interaction strengths are not derived out of any fundamental quantity yet, so they have to be treated as handed out to us by nature as primeval quantities or pristine quantities when you start building your particle physics theory.
Okay. So I think, sir, the last question here is interesting by Orghodip Shaha. So is time symmetric? So that is one of the diagrams that you had shown. So maybe he's asking about that.
Okay. Time symmetric is not very well formed. Let me say this. Time symmetric means if you, for example, go back in time, do things change? Is a question that you can ask. As I said, the laws of mechanics are nature are time symmetric, but there are arrows of time seen in various physical phenomena. For example, in thermal phenomena, they are certainly not symmetric under reversal of time. As I said in my example, you put a hot and a cold body together, then they will gradually become of equal temperature. If you run your clock backward, you never see the reverse happening. That's to say, two bodies with equal temperature in contact with each other, one becoming hot and the other becoming cold without anyone interfering from outside. So therefore, thermal phenomena define an arrow of time, which is an asymmetry in time evolution. Similarly, the universe in which we reside is expanding. That is unquestionable now. And it is also established over the last nearly 20 years that such expansion is slightly accelerated expansion. Now, this also defines an arrow in terms of cosmology. So, there are more than arrows, one, asymmetries or arrows of time already handed out to be handed out in nature, and we cannot talk about that.
Okay.
Now, I have lost track of questions in the chat box, so I need help now. Now, there
Yeah,
are
me
so many
too.
that I am missing
So many
many.
questions. So what is this talk about horizontal symmetry? So this is, I don't understand. Dr. Krishnonath Bandopadhyay.
Oh, he is a very old friend of mine. I didn't know he is there. I'm really fortunate that he is listening to this talk. So, my greetings to him first. So, Krishnanath, my greetings to you. This is probably not the place to talk about horizontal symmetry. In the slide which I showed, where I showed, say, electrons, muons, and taus as repeated particles in a pattern, mass going from lower to higher values, electron, muon, and tau, gradually higher mass, all other properties, charge, angular momenta, etc., being the same. This shows a pattern. So there has been an attempt to explain this by proposing a symmetry among the various what are called families of elementary particles, spin-half particles. Such families are in the quark sector as well. So this is also not proven, but this has been a rather creative speculation that could this be the result of a symmetry, and details of these kinds of symmetries is beyond the scope. So I'm not using the language in terms of a local symmetry, like electromagnetic interaction was formulated in the form of in terms of a local symmetry, like I described. So there have been attempts to study horizontal symmetry or this pattern of fermion families in the form of a local symmetry, and that is horizontal symmetry. No evidence for that yet, but who knows? I mean, this may lead us to some very new perspective of this elementary particle world.
Okay.
Now I
So
have
he
lost
says,
questions. What is there? I'm
uh,
just.
can we consider time as change in space? Okay, so this is a vague question. I don't understand.
Sorry. What is the question?
So there is Shayun Shorkar has asked a question: can we consider time as change in space? So this is a vague question. I think I don't understand the question.
I also don't understand. All I can tell you is that if you are familiar with Lorentz transformations, which is the transformation law of space and time coordinates in special relativity, then with respect to a static observer, if you have a moving observer, for the moving observer, the position and the time coordinates will be different from those in the static observers. And the newly defined time coordinate in the moving observer will be dependent on the spatial coordinate in the static observer. So that way the transformation of time in a different observer or different reference frame may depend on the spatial coordinate. This much I can answer. Beyond that, it is below my beyond my capability.
Okay, I think, sir, you have already answered fairly many questions. So I don't know whether we take more questions or
No, I can take more questions, but I have lost track of them in the chat box because there are many which
yeah,
I
there
may,
are many questions which are coming. Yeah.
yeah. But anyway, it is fine. I mean, here I need help from the organizers also. First of all, you may have a finite time at your disposal. I also have some finite time. I have another appointment soon.
Okay, thank you,
Oh,
sir.
acha. I see. I can see one curious question. Is there an antiparticle related to Higgs boson? The
Yeah.
answer is, if you take the Higgs boson the way it is proposed in the existing theoretical model, it is its own antiparticle. That is to say, there is no separate antiparticle for the Higgs boson. That is not true of all elementary particles which are electrically uncharged. For example, a neutron can have its own antiparticle called an antineutron. That is because the Higgs boson is spinless. A spin particle has its magnetic moment and such things reverse when you come to the antiparticle. But in the case of a Higgs boson, it has no charge, no spin. So there is no property that can distinguish from its antiparticle from itself.
So I think Shujoy Shaha again has an interesting question which is very
Tau
specific.
theta puzzle.
So is it possible for to give some explanation about tau theta puzzle in a point of view of symmetry breaking? This is very specific, but
Okay, I can answer, but the answer I don't think will be understandable to everybody. Tau theta, it takes us back to history. We are talking about 1950s. At that time, two particles were seen of very identical character, but decaying with different lifetimes. One of them was called the tau and the other was called the theta. Later on, there were various manifestations of what are called K mesons, but let's not talk about that. So the very fact that two particles, tau and theta, are not the names of any elementary particles now, they have been given other names in terms of K mesons, which are composite elementary particles. But initially in the 1950s, people were seeing two identical looking particles, but one was decaying in one particular set of lighter particles and the other was decaying in another particular set. If this had to happen, then the puzzle was that the decay process, which was weak interaction, the decay process would have to be parity violating. This is how people first suspected parity violation in weak interaction. The fact that parity violation is there in the electrons that emerge out of beta decays, what a later verification. The experiment was carried out by a lady called Madam Wu, who carried out that experiment and found out that the electrons have a definite spin orientation. But even before that, the explanation of tau theta puzzle first gave an answer to the question by saying that there is parity violation in weak interactions. Two students in the University of Chicago, they were still doing their PhDs and they were not much older than the many of the participants in today's talk. They were two Chinese students of Chicago. Both of them have become celebrated physicists now. One of them had the name T.D. Lee and the other had name C.N. Young. They worked together to give this explanation in terms of parity violation. Both of them got the Nobel Prize together.
Okay, thank you, sir. Once again, on behalf of Physics Department of Ashutosh College, for spending your valuable times in this webinar. Thank you.
Thank you very much for
Okay.
listening to me and for arranging this talk. I'm very happy to be with everybody. Of course, not as happy as I would have been to be physically present in an audience, which is much more inspiring. But still, I'm very happy that people participated in such a long discussion.
Sir, maybe next time we will
Sure.
wait.
Thank you very much, everybody.
Now I request Dr. Amit Kumar Bhattacharya of Physics Department to deliver his vote of thanks.
Okay, thank you, Orpita-di. So, on behalf of the Physics Department, Ashutosh College, I would like to convey our heartiest thanks to our honorable speaker, Professor Vishwarup Mukherjee of IISER Kolkata. Thank you, sir, for delivering such an interesting talk and spending your valuable time with us. Having so many intriguing questions, and there are many questions left out, I can see that the audience has thoroughly enjoyed your lecture on symmetry and broken symmetries in the macroscopic and microscopic world and in the context of elementary particles. At this point, I would like to thank Dr. Manas Kobi, Bursar of Ashutosh College, for supporting this event, and I convey our sincere thanks to the Vice Principal, Professor Apurva Rai of Ashutosh College, for inspiring us and providing the necessary timely support whenever it was required. Support of Internal Quality Assurance Cell of Ashutosh College, who are also the joint collaborator of this webinar, is thankfully acknowledged. In particular, Professor Tatakato Rai Choudhury for delivering the welcome note. I also thank the social media and website management cell for their assistance to set up and conduct this webinar. Last but not the least, we are thankful to all the members and students of the physics department who have actively participated to make this event a grand success. Thank you everyone and thank you all.
My thanks again and my apologies to those whose questions somehow I missed in the chat box or otherwise. I wanted to answer all questions, but in this kind of a webinar, it is inevitable that some error will take place. So I apologize to those whose questions I could not answer.
Okay. Thank you.
Okay. Thank you, sir.
And
Okay.
thank you, sir. And
Goodbye,
thank you,
everybody.
Thank you.
Now,
Goodbye, everybody.
Okay.
okay,
Goodbye,
goodbye.
Bye.
Now, I just want to thank all the participants for their cooperation, which makes the first day of the webinar successful. We will meet again tomorrow at 3 p.m. For another talk, which is about the quasi-periodic order in physics. And the speaker is Dr. Arunabha Chakraborty of Presidency University. We will wait for the tomorrow's talk. Okay, thank you. Thank you all.
Thank you all.